joining us today. We sincerely appreciate you taking your time out today and join us and learn a little bit about the refrigeration system and the cycle itself. Kevin did a great job with the high side portion of the system the last couple days, and I'm going to touch on the starting with the expander valve, the low side of the system, all the way back to the compressor. So thank you very much again. We sincerely appreciate your time. Let's see here. Today we're going to start off with the expansion valve. So the expansion valve, let me go back to the compressor. The compressor actually takes your suction pressure, whatever that pressure may be. We'll say in this case it's maybe 50 pounds suction pressure and stuff. It pumps it up to a pressure, and we'll say 200 pounds. But it pumps it up to a pressure to a point to where we have to bring it up at least 20 degrees above your ambient conditions so that we can remove that heat from the system that we absorb not only from the evaporator but also what was produced in the compressor itself. Keep in mind compressors are, and one thing I didn't talk about this the other day, but compressors are vapor compressor pumps. They are not liquid pumps, right? And we'll talk a little bit and touch a little bit about superheat in a few minutes, but mostly we talk about superheat in next week's class, all right? So in this case, we have your expansion valve. It actually creates a pressure drop from the high side down to the low side to where we can get it to a point to where the suction pressure is at least 10 degrees cooler than the box we're trying to cool, so that we can absorb that heat from the space to carry it back to the condenser and remove that heat out, right? All expansion valve systems pretty much coincide or work together in conjunction with the receiver. And the receiver's function really is to make sure that we have constant pressure or enough liquid to feed the expansion valves to cover the amount of load that the evaporator itself sees. Let's see, where do I want to go with this? So as a load, and we also talked about and touched briefly yesterday on load. What is load? Load is the heat in the space we're trying to pull out of the space to remove it, right? So load is induced. The more load that we have in the space that's induced on the evaporator itself, your expansion valve senses that and opens it up a little bit, or opens it up almost to full capacity if we have a 100% load on that's been induced on the evaporator. And our liquid level in the receiver will actually drop. Okay, it lowers down a little bit. But if our load itself on the evaporator is low, then our load or our receiver, the liquid in the receiver actually goes up a little bit. So they both work, they coincide with one another and work in conjunction with each other, the receiver and the expansion valve system. All right, let's take a look at the expansion valve. Primarily, we have four forces that work in conjunction with each other for this valve to be what I call in equilibrium during normal operations and stuff. And one of the forces we have is the P1, which would be the bulb, the power head assembly with the bulb, and this is pressurized. At the power head itself, we have a diaphragm that's right in the middle of that's sandwiched in between two discs pretty much, and from the top portion of that diaphragm, it's pressurized all the way down to the bulb. Now here you see a little bit of absorbent that we have that we place in the bulb. A lot of times that absorbent is used for to either slow down or speed up the reaction time of the valve itself, mostly primarily to slow down the reaction time of the valve. So so the valve is not acting erratically, opening and closing, or trying to make an adjustment, not necessarily opening, closing, but you know, bouncing up and down, primarily just trying to follow the load of the evaporator. Here we also have an external equalized. This valve is an external equalized. We'll talk about that in a minute. This valve over here that we had in the system is an internal equalized expansion valve. There's a difference between the two. And this one here is an external equalized expansion valve. External equalized expansion valves are used on systems where the evaporator creates a large pressure drop and or we're using a distributor of whatever sort. It could be an orifice style distributor or a Venturi distributor, and we'll talk about that in a minute. So let's go back to the forces here. So we got the bulb force or the pressure force that's pushing down on top of this pin that's trying to either open the valve or close it. So what happens is this bulb actually reacts with temperature. So the warmer this bulb senses, it actually heats up, or not heats up, but it increases the pressure that's inside the bulb itself and causes it to push down on the diaphragm to want to open up this pin, or push the pin down to open up the expansion valve. P4 is another pressure that we take into consideration and that's your liquid pressure coming in from the high side portion of the system. P2 would be right here, would be your evaporator pressure, and then P3 is the only force that we have that we can make, or that's adjustable by the service technician. And that adjustment is to adjust for superheat. And what is superheat? Well, we didn't really talk a whole lot about superheat in a sense last couple of days. We'll talk a little bit more about it next week and touch what superheat is and how it affects the system. Okay, so, but we have these four forces. P1 and P4 is trying to open the valve. P2 and P3 is trying to close the valve. But if the valve is, like I say, in equilibrium and stuff like that, the valve works, with all these forces in equilibrium, the valve works as it's supposed to. By the way, the power head on this valve in particular is removable. Some expansion valves do have power heads that's removable, and some of them are not removable. They're actually a part of the system or part of the valve itself, and you cannot remove those. But here's a little service tidbit for you, for the technicians that are out there and stuff like that. These power heads can go flat, and in a lot of cases, in many instances, if the valve's been in the system for a very long time, there's no reason to change the valve out unless there's been a burnout in the system, a compressor burnout and stuff, which produces a lot of waxes and acids and everything like that. Waxes get built up into the seat and the port area right here. You can take this valve apart and clean it rather than replacing the valve, but I've heard it said that the two main components that people like to replace most in the refrigeration system is not only the compressor but the expansion valve, and a lot of times neither of them have to be replaced, especially if the power head that's gone flat. And how that happens is your diaphragm going up and down with the pressures that it sees in the evaporator and such, it can create a crack, and if it creates a crack in the diaphragm, this pressure that's inside the bulb actually blows out and goes to the low side of the system. When that happens, this valve has no force to push the valve, or the bulb has no force to push the valve open, and it actually starves the coil. So that's a good indicator. How you can test that is actually take the bulb off the system and hold the bulb in your hand and see what the reaction, if there is a reaction with the system pressures and such. See if it feeds. All right, we're going to take a look at what kind of effects we have with a condensing unit that has fan cycling. Now this is a conventional, what I call a conventional expansion valve. The conventional expansion valve, as opposed to what we saw earlier, this is a balance boarded expansion valve. It has one pin that goes and protrudes up to the top of the valve itself. So when I remove the the power head, if I see one pin, I know that that is a balance ported expansion valve. This is a conventional expansion valve. If I pull the power head off the top and I see two pins pushing up through the top of the power head, it is a conventional expansion valve. Conventional expansion valves work a little bit different than your balance ported expansion valve. And here I will illustrate this using this set of slides here. So we have a condensing unit that cycles head pressure at 150 and 100 and 200 pounds PSIG. And that correlates to whatever your ambient temperature is. So if your ambient temperature goes up and the corresponding pressure is above 200 PSIG, the fan will cycle on and try to keep it at around 200 PSIG. When your ambient temperatures fall below, say we get down to wintertime or so, your pressures can fall below 150 PSIG. If that's the case, then we would shut the fan off so that we make sure that we get adequate pressure feeding the expansion valve, because we want to make sure that we have adequate pressure feeding the expansion valve. So we take a look at what happens with the pressure at 150 pounds. That the inlet pressure, again, 150 pounds. Your suction pressure itself is in this case, is 50 pounds PSIG. That's your corresponding pressure at the evaporator. So your pressure drop across this valve itself is 100 pounds, right? And force equals pounds per square inch, which is your force. So you're looking at about 100 pounds of pressure or force pushing down on this pin, trying to cause this pin to open up, okay? Now let's take a look at what happens at 200 PSIG. Fan turns on, kicks on, tries to stay and maintain a minimum of 200 PSI if we can at high ambient conditions. Your head pressure increases to 200 PSIG, and your delta across the expansion valve becomes 150 pounds. So what happens is we're looking at pretty much an unbalanced expansion valve under these conditions and stuff. So back in the 80s, I want to say it's back in the 80s, expansion valve manufacturers developed what we call a balance ported expansion valve, and mainly used primarily for supermarket applications, where at that time we were allowing the head pressures to float a little bit. When I say float, it's following the ambient conditions. So during the winter time, we were allowing the head pressures to drop a little bit down to 150 pounds per se, and then above during the summertime, it would climb up to roughly 200 psi because of the ambient temperatures and stuff. And so we would call that floating head pressures. We're allowing, and the only reason why we did that primarily is for energy saving energies. But as your inlet force or inlet liquid pressure comes into the expansion valve, with the balance ported valve with this one pin, this area right here is the same as the area that's down here on the pin. When the liquid pressure comes in, it hits this pin, it basically pushes on both sides of these surfaces, and that pressure, hence the term, balances out. And the other day when I was talking about expansion valves and stuff, that force that we see, which was the P1 or P4 coming in, pushing down on the expansion valve, that force for the balance ported expansion valves then becomes negligible somewhat, okay? So again, we get smoother operation for head floating, floating head pressure systems, and also condensers that have fan cycling and stuff. So, which leads to a question that I always pose when we're giving the class: Can you, if a contractor comes into the store and has a conventional expansion valve, Can you substitute that conventional expansion valve with a balanced ported expansion valve? And my answer is always yes, you can. But if a customer comes in with a balanced ported expansion valve, and the only valve that you have is a conventional expansion valve, I would say I wouldn't do it. And the reason why is because the operating range on the balanced ported expansion valve can operate down to about 25% of its rated capacity, and those are rough figures. Whereas a conventional expansion valve, maybe 35, probably 40% of its rated capacity and stuff. So you get a better range with the balanced ported expansion valve. And which also leads into another question: so if a contractor comes in with a expansion valve that has a internal equalized valve and he wants a replacement, can I replace that expansion valve with an external equalized expansion valve? And I would say yes, you can, but make sure you plumb that quarter-inch line from that port on the side of the expansion valve into the suction line just past the bulb. But having said that, at any rate, you know, always replace like for like if you can, if that's the option. That's the best option you can go with. So ARI came out with some capacities and such. In a sense, in a lot of ways, when you take a look at some of the boxes that are on some of the manufacturers, they have an ARI rating for the valve itself, and that's a nominal rating, right, for the valve, not only for expansion valves but also for solenoid valves as well. And my point here is, if a customer does come in or a contractor does come in with a valve, or he wants you to select a valve maybe over the phone and stuff, make sure you get all of the conditions that he's working with. Otherwise, you can oversize the expansion valve just by looking at the nominal ratings. So let's go through a couple steps here for expansion valve sizing and selection. We need to know a couple things prior to the selection. We need to know what refrigerant type we're working with. That's very important, right? We need to know the evaporator temperature that the evaporator is operating at, the capacity of that evaporator. We also need to know what the condensing temperature is so that we can correlate over to the pressure itself. Same with the evaporator. We need to know what the evaporator pressure is. We need to know the liquid temperature feeding the expansion valve. That's really important, especially on some of the R404A systems. We'll talk about that in just a second. And we need to know if there's a distributor that's being used in the system, right? Because there's a pressure drop induced by that distributor. For the most part, and then what's very important with this is we do not want to size the expansion valve to the compressor. We always want to make sure that we size the expansion valve to the evaporator. That's the load we're working, that's the load that we see that we're trying to maintain, and not what's being produced by the compressor itself. All right. So let's go through this, take a little bit further. We also need to know what the net pressure drop is across the expansion valve. That's really important. So depending on what kind of system you're working with will dictate what your ambient temperatures are, which would be the corresponding or the correlating pressures, right, with the temperature. We also need to know if there's a distributor, again, orifice type distributor, and that would be like the Sporlan. They manufacture some of the orifice type distributors, very common in the industry actually, that has nozzles that are built into the distributor and are removable and stuff. We will talk a little bit more next week on that style of distributor. And we also have the Venturi type distributor. Both of those produce a pressure drop across that we need to take into account when we're determining what the net pressure drop is across the valve. We also need to know what the pressure is at the evaporator, right? and that's we need to know that information in order to get the net pressure drop. So we have a couple scenarios here, actually, three scenarios with 3 different applications, actually, and we'll go through some calcs here to see what the net pressure drop to determine what the net pressure drop is across the expansion valve. So here's a system here with no distributor, but we're not going to take into account, or we're not going to take into account not only the liquid line pressure drop, but also the components that are in that liquid line. We're just going to look at the pressure drop, net pressure drop across, and discounting any of this other information here. So in this system, we have an R404A, no distributor, right? Evaporator is plus 20 degrees. Condensing temperature is 110 degrees. So at plus 20 degrees, our pressure at the evaporator is 55.6 pounds. And then at the condenser at 110, using the PT charts, and that's one thing, a disadvantage with this class, given this class over a webcast, is it doesn't give us an opportunity to really review and look at what a PT chart is. However, when you do have time, take a look at the PT charts, and you'll have corresponding pressures and temperatures that relate to the saturated conditions that are happening in both the condenser and also the evaporator. So our condensing temperature is 110 degrees at 271 psig. The difference between the two then would be net pressure drop, or the pressure drop, not necessarily the net pressure drop, but the pressure drop across that expansion valve is 215.4 psi. Now let's take a look at a system that has a distributor. So again, we have 404A refrigerant, and this time we're using a Venturi distributor right here. Distributors are used for systems that have multi-circuited evaporators, maybe a 6-circuited, 10-circuited, or whatever it may be, multi-circuited evaporators. And we touch about and talk about this more in depth and in length next week in the 202 class. So here we have a distributor. We're taking into account it has 15 pounds pressure drop across that. The evaporator is this time at minus 20. Condensing temperature is 105 degrees. So at minus 20, our pressure there using 404A is 17 psig. The condensing temperature at 105 is 254 psig. Excuse me. I just had a big bowl of oatmeal. Yummy. Anyway, so we're looking at the pressure feeding the expansion valve is 254 psig right here, okay? And we add up the both the distributor and also the suction pressures, and that gives us a pressure of 32 psi. When we subtract 32 psi from 254, we get a pressure drop of 222 psi, okay? Our last scenario, we're going to actually take a look at the pressure drop that's induced or produced actually by your the filter dryers, the solenoid, and also your sight glass, along with the your liquid line. So again, take the same system. We're looking at 404A, Venturi pressure distributor again. Evaporator pressure, pardon me. Evaporator pressure is minus 20, and condensing is 105. High side losses is, we're looking at 10 pounds for the high side losses. Again, our condensing pressure is 254 psig, and at 254 psig at the condenser, before it hits all of these other components, by the time it leaves those components and gets to a point where it's actually feeding the expansion valve, we're now looking at 244 psig with that 10-pound pressure drop, again, taking into account all these components and also the liquid line. Again, our evaporator temperature is minus 20. It equates to 17 psig. We add the 17 plus the 15, and that gives us now a net pressure drop of 212 psi. So we want to use this information for selecting the valve, and we're going to go through some charts here, right here. But we're actually going to select a different type of system using R22 as a refrigerant, not necessarily 404A. So we'll go through the valve selection process right now. So we know that it's an R22, and this is looking at the extended charge rather than looking at the box that's printed, the label that's printed on the side of the expansion valve box again. Okay. Again, it's preferred that you actually go to the extended tables to cover yourself so that you don't mislead or missize the expansion valve and or the solenoid valve in the system. So we're looking at plus 40 degrees evaporator temperature. All right. Our net pressure drop in this case is 100 psi. So remember I talked about earlier how our fan cycling for the condensing unit it was operating between 150 to 200 psi. So what happens with when we increase our pressure, the condenser itself, we actually raise the capacity of the expansion valve just a little. So that valve, I'm not saying it's going to be grossly oversized, but it could be oversized in that type of application. And if that's the case, it could actually get to a point where it may hunt a little bit at low load conditions or whatever. Low load conditions specifically at higher ambient conditions. All right, net pressure drop, 100 psi. We're looking at the liquid temperature at the inlet is 100 degrees. Now, 100 degrees, there's no multiplier added to this liquid temperature. If it was an R404A system, you're actually looking at a 1.5 multiplier at 50 degrees liquid temperature. Now, our X-line units, the XFAL units, they have a built-in liquid line heat exchanger, right? And we're doing a couple things with that liquid line heat exchanger. I won't get into it in this class. Tune in on Tuesday and we'll talk a little bit more about that possibly. But we can possibly send out liquid temperature feeding the expansion valve at 50 degrees. If that's the case, and that's on those XFAL units, and if that's the case, our expansion valve could be grossly oversized in that sense that if you have a 10-ton valve on a 10-ton evaporator and such, and we're feeding that liquid temperature at plus 50 degrees, we now have a 15-ton valve feeding that 10-ton evaporator, and we could have some problems overfeeding the system and flooding back to the compressor itself. So if you have an existing system that has that's a low temp system and they want to use the XFAL unit, make sure that they resize and reselect the expansion valve on that evaporator. Otherwise, again, it could be grossly oversized and we could overfeed and slug back to the compressor. So back to our selection here. Required load in tons, we're looking at 3 tons. So in this case, we're selecting an expansion valve that's rated at 2.75 rather than 3.37. And I prefer to undersize the expansion valve just a little bit. And the reason why is because on low load applications at the evaporator, if we have an oversized expansion valve, we can overfeed the the evaporator, whereas the expansion valve could hunt. We can get into a hunting condition there, and we don't want that to happen. So I personally would rather undersize the expansion valve just a little bit with the evaporator, just so that when at full load conditions, that expansion valve is wide open and feeding and doing its best as we can to feed that evaporator. Then on the downside, or the downside portion of this, when the load conditions actually apply to the evaporator, then we won't have to worry about any hunting conditions in that case. So in this case, we've selected the 2.5. So again, had I selected the 3 by using the nominal ratings that we have from ARI, this valve probably would have been oversized. All right, so that this kind of supports my point that it's always best to size and select the expansion valve rather than looking at what's on the side of the box for nominal conditions. Here we have a cap tube system. You know, metering devices come in all different types of sizes, and this is, again, is one of the 4 main components that's in the system, right? The metering device. We can have a TXV, which we've talked about, thermal expansion valve. We also have automatic expansion valves, hand expansion valves used in large ammonia systems and stuff. We also have electronic expansion valves. In our case, we have some really good expansion valves. The EX4s through the EX8 electronic expansion valves that White Rogers manufactures and sells. We also have just a standard orifice or the cap tube. Cap tube, this system here is what we consider a critically charged system. It's designed to, notice there's no receiver over here, right? So on a system like this, it's not necessarily, we don't need a receiver because the load itself on the evaporator is pretty much constant, right? So, and in addition to that, these compressors that we have on these critically charged systems are primarily low torque starting compressors and stuff. Really small, like your refrigerator that you have on your house or at your house, not on your house. At your house. Okay, so when the system goes in the off cycle, when the compressor shuts off during the off cycle, our pressures equalize throughout this whole system, right? Whatever that standing pressure may be. And when it goes to restart, we can use the low starting torque compressor to operate these type of conditions rather than a condensing or compressor that utilizes a starting capacitor and even or a run capacitor on this system. But again, these are a critically charged system. I have seen some reach-in true cases, those reach-in refrigerators, where guys have came out and they didn't have the cap tube at the wholesale house. Not sure why. They didn't have a cap tube at the wholesale house, and rather than using a cap tube, they installed the expansion valve. We could have lots of problems if you have an expansion valve on a critically charged system, especially when they open up and close those doors, because we're creating a load on the evaporator that could cause the expansion valve to open wide up and flood back to the compressor. And the other day I talked about the K-body compressors that are used in the true type reach-in refrigerators and stuff, and that's a air-cooled compressor. That compressor can take a direct liquid slug into the head of it and destroy the compressor. So again, replace like for like if you can. If they have a cap tube system and you feel that it's plugged, you can remove that cap tube, take it to the wholesale house, and they can match it up and replace it like for like if you can. Now let's talk about capacity control at the evaporator. What we have here is what we call the hot gas bypass, along with the solenoid valve here in series with the hot gas bypass in parallel to the liquid line solenoid valve. And this valve here is it senses outlet pressure. And the way this works is when our load, we talked about load in the space, if we're operating at 100% load on our expansion valve is wide open, and we're feeding this evaporator as much as we can with liquid refrigerant. All right, when our load starts to fall off, say we went from 100% down to about 25%, our compressor could possibly cycle on and off when it sees that, because we're at low load conditions and stuff. The compressor will cycle. So what we do is we create a false load into the evaporator. And so this valve has a tap on top, not a tap, but an adjusting stem on top where we can adjust the valve to match whatever pressure we want the valve to open up at, so that we can we inject actually high pressure gas or a little bit of hot gas into the suction side of the system right before the evaporator. And we also want to, that's the best place for it. I have seen some before where they actually inject after the evaporator, and I prefer that you inject it in between the evaporator and also the expansion valve, because the expansion valve will sense that additional heat at the bulb itself and open up a little bit more to compensate for that heat that's induced by the hot gas bypass. But again, we're creating an artificial load to keep the compressor from cycling on and off. We also have the solenoid valves that are in parallel to each other, and what we want to do here is make sure that they're tied into each other, so when the system does go into off cycle, that they both shut off at the same time, so that we don't, and if the compressor goes into the pump down, we can pump down both this side and also the liquid line past the solenoid valve. Okay. All right, let's talk about some evaporators. We didn't really talk about evaporators, but here we have, we're using the Russell nomenclature on this, and we're going to go back to our ARI nominal conditions and nominal settings, and the nomenclature that's used in the ARI nomenclature. So the model of this is what we consider an all-temp model. It's an air-cooled. It's got this one has one fan. It's 8 fins per inch and 41C. This 41C, using the ARI nominal ratings, kind of corresponds with what we see here with the at 10 degree temperature difference between the evaporator and the space. So in some cases, if you're out in the field and you're trying to figure out what the capacity is on an evaporator, the nominal conditions, a lot of times that information is built into the nomenclature of the coil itself, the evaporator, right? So 106, 106. Of course, when we change the conditions for the temperature difference across the evaporator, those capacities change. All right, let's talk about EPR. Another term for the EPR valve would be an inlet pressure regulator. A holdback valve, I've heard terminology out in the industry with a holdback valve or back pressure regulator. And it's located in between or right after the evaporator, but in between the evaporator and the compressor. And how this works is these EPRs, they control inlet pressure only. And the way this works is you have some bellows here that's built into this portion of the top cap of the valve itself, and you also have a disc that rides on a seat area right here. Okay, and normally in off, when the compressor is in the off mode, this seat or this disc will actually close up and fall on the seat right here. And but if you take a look at the disc area right here is the same as the bellows themselves. the square area. And in that sense, when this pressure right here is the forces that's pushed on these both the bellows and the disc, because the areas are the same, this pressure cancels out. We don't really see this pressure or the forces on these on the bellows and the disc. They don't play an act on this valve itself. So the only forces that we see really is the inlet force coming from the evaporator, the pressure, and also the spring, which is adjustable here, kind of like the superheat spring on the expansion valve. But it is adjustable, and you take off the cap, you put your Allen wrench down inside here, and with the system in once the system is in has been operating for a long period of time and stuff, and it's at low load conditions or whatever it may be, you can actually tap onto or put your gauges onto the tap right here and make your adjustment. Of course, if we turn the wrench clockwise, we're going to increase the force, and we're going to increase the pressure and up the pressure setting on the valve. And when we counterclockwise with this with your tool, then it reduces and lowers the pressure setting on that valve. So where would this? Why would I want to use this valve in the system? Let's say that maybe we have, and rather than this being a frozen meat, maybe this is just one evaporator and not three of them. We'll hit this in a minute. But maybe we have just one evaporator right here, and it's a deli case lineup and stuff. And we want to make sure that this deli case lineup doesn't freeze. We don't want to freeze any of the meats, and or if it's a dairy case lineup, we don't want to freeze the product that's inside the case and stuff like that. So what we want to do is we install an EPR on this system, and that actually prevents this evaporator from dropping below 32 degrees Fahrenheit, so that we don't freeze up the product that's inside the case. We make that adjustment here at the valve. We set the pressure setting, and whatever the pressure setting is corresponding to or correlating to the temperature, that's how we make that adjustment, and we can adjust that to prevent. It's really a safety in that sense that's used for the deli and those cases and stuff. Again, it's to protect the product. So here now we're taking this lineup here, and we have three cases, and maybe the system's in the off mode, and the compressor, or we're just doing a startup, commissioning the case lineup and stuff. We're doing a startup. Compressor starts up, and we're at 200 pounds or so. And as it gets down to an area where that pressure is the same pressure that corresponds with the temperature here at plus 20, this valve will start to open up if we set it. If we've already set the settings on these valves at minus 20, minus 30, and minus 35, this valve will open up first, right? And it'll start to regulate and regulate the evaporator to where this maintains and stays at minus 20 degrees. The compressor will continue to cool down until, again, we get to this the walk-in freezer, and then this valve will start to regulate and maintain a pressure corresponding to a minus 30 degrees at the evaporator here. And then it finally gets down to the pressure to where we can actually operate the ice cream at minus 35 degrees. In many cases on a situation like this, we can actually eliminate this valve per se, and we can just run the system off of the low pressure control on the house pressure. This would be a good example of how these evaporator pressure regulators work in a system on the low side and also the medium size for a supermarket application and stuff. Here's a situation where we have one evaporator is much smaller than the other evaporator, but we're both running at plus 25 degrees, medium temp. right? So rather than, if that's the case, then we would suck down the pressure and the temperature on this evaporator more so than we would on this evaporator right here. So to prevent that from happening, we put in an EPR valve on the unit here to protect that from happening. And it's, again, it's about protecting food spoilage and stuff. Another valve in that, pretty much in the same area, right before the compressor, is what we call a CPR, which is a crankcase pressure regulator. Crankcase pressure regulator is an outlet pressure regulator, senses outlet pressure, and the only reason why we have that crankcase pressure regulator in the system is to prevent the compressor from overloading, especially on a system where we don't have a pump down cycle in this system, where there's a solenoid valve and also a receiver. So if this system didn't have a pump down cycle and stuff, when the compressor shuts off, we'll have too much pressure over here, and when the compressor goes to start up, that inrush, the amount of gas coming back to the compressor, creates an overload and shuts the compressor off and can cycle the compressor. So to prevent that from happening, what we do is we install a CPR, crankcase pressure regulator, in the system, and that helps regulate the pressure coming back to the compressor so we don't overload the compressor during startup. The next valve we have in series with the system would be your ball valve, and here we have a rack scenario here with some lineup, some header. Here we have we have some sorts here, which are the EPR valves that are on the cases, and in series with the sorts we have some ball valves, and the ball valves is a full ported valve internally. When this valve is in this direction, that means that this case lineup is operating. However, when we make an adjustment and use our wrench to turn this valve in this direction, we actually close off. We can isolate this area if we need to work on maybe the evaporator or the expansion valve or whatever it may be and stuff. But it is a full ported valve, and which creates a very minimal pressure drop across that the valve in the suction line, and that's what we want to see. That's a very low pressure drop, especially on really low load or really low temperature applications. The next in line we would have would be the suction line accumulator. And the suction line accumulator is there to prevent liquid slugging or liquid coming back to the compressor if our valve is maybe grossly oversized or whatever it may be, and we're hunting. We may be sending off liquid back to the compressor, which could cause the compressor to slug. Again, these are vapor compression pumps, and pumping liquid can be detrimental to these compressors, right? So we want to make sure that we get nothing but vapor coming back to the compressor to protect the compressor. So the way this works is we have the inlet portion of the inlet stub coming off the top of the accumulator, right? And that's offset this J tube right here. So, and you can see that it's not only offset, but it's just plumbed in right at the surface of the top cap of the suction accumulator. Our J tube, actually, this is going back to the compressor itself, but what it does, again, our velocity coming back to this accumulator is roughly 500 to 700 feet per minute. When it hits this accumulator, it slows way down, right? Because we have a wide spot in the line. It slows way down. Our velocity slows down, causing the liquid, not only the liquid refrigerant, but also the oil to fall and collect at the bottom here. Therefore, we only going back to the compressor would be the vapor that we collect at the top of the accumulator this pitot tube, or this hole down at the bottom of here, we can pick up both a liquid refrigerant and also oil, but it's at a predetermined rate to where we're not going to cause any damage going back to the compressor. So if it does have any liquid refrigerant that we are picking up, hopefully by the time it gets back out to the suction side of the system, it does boil off in the, so in a sense we're really just bringing back oil. For every 1 drop that of oil that leaves that compressor, we want that oil back to the compressor so that we always maintain that proper oil level. Last thing I want to cover here, I don't know how much time we have, but the last thing I want to cover here is the shell the suction line filter dryers with the shell tube type. And really, I see mostly these type of shell type dryers in supermarket applications, large commercial applications, and sometimes some industrial applications as well. And they have cores, so depending on the size of your, or the capacity of your system, total capacity of your system will dictate how many cores you actually have in this canister here. So you may have 1, 2, 3, maybe 4 cores in this canister. So maybe if you have a, God forbid, maybe if you have a compressor burnout or so, after a compressor burnout, if the system's so large enough to where you can't flush it out, a lot of times people will install a suction line filter dryer in there to try to capture some of that acids and the waxes that are built up in the system to protect, again, to protect the compressor, right? Our number one goal is to keep that compressor running, the heart of the system. So again, you can, depending on the size of the canister itself, will dictate, or the capacity will dictate the size of the canister, will also dictate how many cores that you put in. We have different cores for right after burnout. We have standard cores for maybe high moisture, other cores for right after burnout, maybe for acid control and wax and stuff. Once you feel that you may have a clean system, what I would recommend is, especially after a burnout, come back after a 24-hour period. A lot of times we say 48 hours, but if it's a low temp system, anything below -10 or even 0 degrees, I would actually make an attempt to come back to the job site 24 hours after I've installed the filter dryers, just so that I can check the pressure drop across the canister to make sure that it doesn't exceed anywhere from 2 to 5 pounds. On a low temp system, I would look at maybe 2 pounds, and if it's 2 pounds, then I would either change out the cores, change out the cores and put more cores in to see if we can clean up the system even more. And once it gets down to a minimum, what you really want to do is check your pressure drop before you start the system, or before you start cleaning up the system, right? So note that, and then after a 24-hour period, make a comparison with that pressure drop to what you initially received during startup. And if it's greater than 2 psi or so, then I would come back and probably change out the filter dryers, the cores, and or substitute that with, if it's a clean system, substitute that with just the strainers. Or you can just eliminate them altogether. And with that, I think we are done. So